All right, this is a review of Physics 1 for my Physics 2 students. And the third and final concept that we're going to use from Physics 1 in Physics 2 is conservation of energy. So, first thing we want to know with conservation of energy is when we talk about conservation of energy, we are always talking about the energy of a system. And a system is just any collection of objects. So when we talk about conservation of energy, it is always the energy of a collection of objects that we're talking about. Now, you could make your collection of objects the entire universe, and then you'd say, okay, the energy of the entire universe. Or you can make your collection of objects a single object, like the energy of, my pen. But anytime we start talking about conservation of energy, it's important to know what is the collection of objects we're talking about, what is the system we're talking about. Okay, and then the other word that we have is environment, and the environment is everything else. If it's not part of the system, then it's part of the environment. Okay, the environment is everything other than the objects that are part of the system. Okay, so that brings us to the concept of an isolated system. An isolated system, for our purposes, has two important properties. There is no work done by the environment. Okay, no work done by the environment. And two, there is no heat lost to the environment. And I should say lost or gained. We don't want to gain heat from the environment. We don't want to lose heat to the environment. That would make it not an isolated system. We also don't want work done by the environment or work done from our objects to the environment. Those would be, again, make it not an isolated system. Okay, but if it is an isolated system, then what that means is that the energy of our system will not change. Now, this becomes an important problem-solving tool when we consider we have this system, right? We've got this collection of objects, and something in that system changes, right? We have some sort of change in the system, and now we still have our system, but it has gone from its initial state to its final state. Some change has happened in the system, and what we can say, though, if it's an isolated system, whatever happened inside the system, whatever change happened, doesn't change the total energy of the system. What that means is that the total energy that the system had before the change should equal the total energy that the system has after the change. Okay, so if it's an isolated system, lots of things can happen in the system. We can have some sort of change happen, but that change isn't going to affect the total energy of the system. Now, total energy, for our purposes, that's going to be kinetic energy, the energy that things have because they're moving, and that's going to be potential energy. And in Physics 1, we had two different kinds of potential energy, springs and gravity. And in Physics 2, we'll introduce some new kinds of potential energy. But the rule is the kinetic energy plus the potential energy plus the other kinds of energy, and that would include thermal energy and chemical energy and nuclear energy and sound energy and electrical energy and all other different kinds of energy, should equal the total energy, that is the kinetic energy, plus the potential energy, plus the other kinds of energy. And so what we're saying is the total energy at the beginning is equal to the total energy at the end, or the total energy that the system had before whatever happens is going to equal the total energy of the system after whatever happens. And in Physics 1, in our textbook, which is the OpenStax textbook, this is often written as KE initial plus potential energy initial is equal to KE final plus potential energy final plus the change in other kinds of energy. And we get this change in other kinds of energy by subtracting this from both sides of the equation, and we get OE final minus OE initial, which is the change in other kinds of energy. Now that's important because oftentimes for problems that are easy to do using energy, this term might be zero. And if it is zero, that makes energy a very easy tool for solving problems. If this is not zero, it makes energy a harder tool for solving problems. So, things that would make this not zero, there are several. Friction. If there's friction in your system, then that takes some of the kinetic energy and converts it into thermal energy. And that means your other energy is going to change. Your thermal energy would increase. Air resistance is another example of something that would make the change in other energies not zero. Collisions. All of these things produce thermal energy. And if you have a collision or you have friction or you have an air resistance, then this change in other kinds of energy is probably not going to be zero. There are other things here, chemical reactions. That's like an explosion or running a gasoline engine or using a battery. Sound or light require energy. So if you produce sound or you produce light, that's going to be other kinds of energy. So there are lots of other kinds of energy, but in certain problems where there's no friction, no air resistance, no collision, no chemical reactions, no sound or light produced, then this term could be zero, and if that term is zero, then these problems become relatively straightforward and easy to solve. So let's do a quick example. So let's imagine that we have a roller skater or a skateboarder, and he is on his little skateboard, and it's on, what is this, a quarter pipe, right? He's on a quarter pipe. And he starts out at the top, and he rides his little skateboard down to the bottom. And we know that he starts out 3 meters above the ground. And he also starts out with an initial velocity of 2 meters per second. So he does not start at rest. He starts out already moving down the ramp. And then the question we have is, how fast is he moving when he gets to the bottom of the ramp? And in the problem's going to tell us, assume no friction and no air resistance. Okay, great. We're going to use energy to solve this problem, and the first thing we're going to do is consider what is our system. And the system here is going to be the man And the reason we got to include the man is because he's moving. So that's going to be an important part of the system. The skateboard. Again, the skateboard's moving, so that's an important part of the system. And then I need anything that is pushing or pulling on the man in the skateboard. So I'm going to include the ramp as part of my system because it's pulling or pushing on the skateboard. And I'm going to include the earth as part of my system because it's pulling or pushing on the skateboard. Using gravity, right? The gravitational force is a force exerted by the earth. But I can't put gravity here because gravity is not an object. Gravity is a force. I need to know the object that's exerting that force because the system is a collection of objects. So here's my system, and my system has undergone a change. We had an initial state for our system, and we have a final state for our system. And because our system is isolated, what we know is that the total energy of that system is going to be conserved. So the kinetic energy initial plus the potential energy initial should be equal to the kinetic energy final plus the potential energy final plus the change in other kinds of energy. Okay, so we'll start with the change in other kinds of energy. Because the problem says there's no friction and no air resistance, and we can see there's no collisions, and we know that the skateboard's not powered by a battery or an engine or any other kind of thing that's like using chemicals, we can say that the change in other kinds of energy is zero, and that's going to make this problem much easier to solve. There's only one kind of kinetic energy. Kinetic energy is always 1/2 mass times velocity squared. So our initial kinetic energy is going to be 1/2 mass times initial velocity squared. Our final kinetic energy is going to be 1/2 mass times final velocity squared. But there are multiple different kinds of potential energy, and you need to sort of check all of them to see if they apply to this problem or not. So from Physics 1, we have gravity, and the gravitational potential energy is mgh, mass times gravity times height. We have springs, and the spring potential energy is 1/2 kx squared, where k is the spring constant and x is how much the spring is either stretched or compressed. And then in Physics 2, we're going to learn about some new kinds of potential energy, but they don't show up in this problem, and neither do springs. Springs don't show up in this problem either, so the only thing I need to worry about is my mgh. Well, for the initial, my mgh is definitely going to be there, mgh initial, and then I guess I can put in plus mgh final. But right away, I recognize that h is equal to 0 at the final. So I'm going to go ahead and cross that one out, because if h is equal to 0, that whole term is going to be 0. Okay, so next I'm trying to find v final. So I'm going to multiply both sides of the equation by 2. When I multiply the left-hand side of the equation by 2, I have to distribute it to the whole thing. So I get m v initial squared plus 2 mgh initial is equal to, and when I multiply the right side of the equation by 2, I get just m v final squared. Next thing I'm going to do is divide both sides of the equation by m. So if I divide the right side of the equation by m, I multiply it by 1/m, and divide the left side of the equation by m. My m's cancel there. And here, again, I have to distribute the 1/m to both pieces of this equation. So when I multiply that by the first one, the m's cancel. When I multiply by the second one, the m's also cancel. So that cancels with that and that. And I end up with v final squared is equal to v initial squared plus 2gh initial. Take the square root of both sides. When I take the square root of the left, the squared goes away. When I take the square root of the right, I get the square root of this. But I have to be a little careful, actually, because when I take the square root of both sides of the equation, it's a little tricky. If I have x squared equals 9, and you take the square root of both sides, you get x equals 3. And you think that's the right answer. But actually, negative 3 squared is also equal to 9. So 3 isn't the only possible answer. It also could be negative 3. There are two answers to that equation. Same thing here. When I have v squared is equal to v initial squared plus 2gh initial, when I take the square root of both sides, that gives me one of two possible answers. But the answer also could be negative the square root of v initial squared plus 2gh initial. And when I go look at the problem, it doesn't really make sense for the skateboarder to be moving to the left, so that isn't really a reasonable answer, but based on just the math, it could have been. Okay, so finally I'm ready to plug numbers into my equation. So my v final is equal to the square root of 2 squared plus 2 times 9.81 times 3 meters. H initial was 3 meters. G is 9.81. Notice I didn't need the mass of the skateboarder. It canceled in the problem. This would be the same answer regardless of the mass of the skateboarder. That's kind of interesting. And we get an answer of 7.93 meters per second for the final velocity of the skateboarder. Now, I want to point out two things about this answer. First of all, the final velocity is faster than the initial velocity, which does make sense to me. If you go down a hill, you should pick up speed. The other thing is 7.93 meters per second is pretty fast. We know that people walk. A walking speed is somewhere between 1 and 2 meters per second. 1 meter per second is a really slow walk. 2 meters per second is a really fast walk. And the world record for the fastest human is about 12 meters per second. His name was Usain Bolt. And when he was running the 100-meter dash, he reached a top speed of about 12 meters per second. So this is closer to the world record top speed of a really fast person than it is the walking speed of an average person. He's moving pretty fast by the time he gets to the bottom of the hill. Okay, so that was conservation of energy. And again, if you want more information, feel free to look back at my videos from Physics 1. But we will be using conservation of energy in Physics 2.